So we've got two speakers this time, which is, I think, the second time we've done two speakers. Annette Lykknes, who's a historian of chemistry at the Norwegian University of Science and Technology in Trondheim. She's also chair of the Working Party of History of Chemistry, European Chemical Society, and chair of the History Group of the Norwegian Chemical Society. And since last year has been chair of the Norwegian Association for the History of Science. And her research interests include, among other things, so history of 19th and 20th century chemistry and university history, especially in Norway, and the history of women and couples in science, which she's published extensively. And when I was sort of going through the brief bios that both Annette and Brigitte and Tiggelen sent to me, it was quite striking how much they've collaborated. So Brigitte is now Director of International Affairs at the Science History Institute, which is in Philadelphia, but I think you spend most of your time in various European countries of promoting Science History Institute. And she's also held various positions of research, outreach, and teaching in Belgium, mostly at the University of Louvain. And they have published extensively. I'll just concentrate on their joint publications rather than individual publications. The periodic system, the multiple values of an icon, that was a special issue of Centaurus in 2019. For better or worse, collaborative couples in the sciences, and women, and most spectacularly, I suppose, women in the element, for which they produced as well a nice little notebook to go with the book. Selected women's contributions to the periodic system, and they're also joint editor of Analysis, Historical Cases in Chemistry, published by World Scientific. So it is therefore highly appropriate that they're doing a joint presentation, Discovering Elements in the Age of Radioactivity, Two Contrasting Stories. And I was particularly interested as a Davy person to see at some point in the 19th century, there was a proposal to name a chemical element Davium, which I think was a really good idea and should have been executed, but there we are. So Annette's going to go first, and then Brigitte, and then we'll have a discussion. So over to you, Annette.
Thank you very much for the introduction. So this talk is based on a forthcoming volume that Brigitte and I have co-edited about the nature of scientific discovery in chemistry, with emphasis on chemical elements. And this is will be the second volume of this analysis book series that you mentioned. So after the introduction, I will present the case of polonium and radium. And then Brigitte will proceed with the case of element 43 and give some concluding remarks. So I'll kick off this talk the way we open our introduction in the book, with a quote from the book 100 Greatest Science Discoveries of All Time, authored by Kendall Haven, who is a research scientist and award-winning science writer, which gives some impression or give a glimpse into the fascination that scientific discovery often brings. And the internet is full of accounts on discoveries in science which testify to this thrill of discovery, and I provide a few quotes here. So as historians, we are used to anecdotal stories from the history of science in popular culture, and we are aware that these stories fascinate. We're also aware of some of the pitfalls associated with simplified discovery histories. And Douglas Alkin has named 3 of them, and he calls it pseudo-history when these aspects are present. For example, if stories heroize historical actors and take their contributions out of proportions, if the stories idealize scientific processes or sharpen actors' roles for the sake of a good story. So what can we as historians do about it, and what are we willing to do about it other than doing our work as usual? As someone working both in the field of history of science and science education, I see the challenges educators face when they want to use examples from history of science and all they've got is the simplified stories. Since the historians' works are not always accessible, perhaps not even relevant for that kind of public. Stephen G. Brush wrote 50 years ago that teachers want their success stories and that history of science might scare them off. and Olkin echoed that publication 30 years later. Some of this might be true, but it is equally true that we historians can do a better job offering nuanced and accessible stories to scientists and science educators interested in using them in their teaching. So the work with this volume was partly motivated by this gap that we see between historians' knowledge and the public's access to this knowledge. And we have framed the introduction with this in mind. But the book is certainly not about presenting old knowledge. Each chapter offers fresh perspective of discoveries of one or more elements based on recent research. But I also bring to the fore the question about how discovery histories come about and how they are shaped through history. So the overall question we ask with the book is the following: how do discoveries and how they are presented matter to the professional historian, chemist, student, and general public? So this is not the first collaborative project Brigitte and I have had together, as Frank mentioned. In recent years, we have been involved in several projects on the history of the periodic system, among others, this book about women and their contributions to the system. And in our work, we came across periodic tables of flags, and this made us reflect about what these kind of illustrations convey about scientific discoveries. In many ways, such tables and what they are trying to communicate capture some of the problematic sides about popular discovery histories. And the idea behind such periodic tables is that in the boxes where we normally see the symbols of the elements, we instead see flags that are supposed to indicate which nations were involved in the discovery. But what do we mean by a nationality? Are we referring to the country in which the discovery took place, or the nationality of the discoverer? Do we mean the country as it has been defined on a modern map, or the country it belonged to in historical times? And more importantly, these illustrations do not offer any information about the processes behind the discoveries, the time involved, the many actors who took part through independent steps, and so on and so forth. Instead, we get the impression that the discovery took place at a certain place and time in history. And that it is extremely difficult, if not impossible, to pinpoint a discovery to a particular time and place, or a person for that sake, like what we are seeing attempted here in this table, is demonstrated in Sarah Hyman's chapter about the discovery of aluminium. And her chapter also reminds us that what ends up as the discovery in historical accounts is, of course, again dependent on what counts as a discovery. Did the discovery take place when the unknown material was first predicted, or perhaps when it was detected, when it was isolated, or when it was mass-produced? And does it matter whether it was produced in quantities that would make it possible to determine properties such as atomic weight, which was the main or the unique property that defined an element long into the 20th century? And even more so in the era of radioactivity, which we will focus on today, since scientists were then dealing to a large extent with imponderables in their research. What constituted a discovery in the age of radioactivity when no balance could be made useful due to the lack of measurable amounts of the substances, at least in the beginning, and when samples were so impure that spectroscopic analyses were initially also difficult? So then we will move to the case of radium and polonium, which is the chapter I wrote in this volume. And that story departs from the well-known story about the Curies' discovery of polonium and radium in 1898 onwards. However, it turns out that the well-known story may not be so well-known after all, or not complete anyway, especially that of polonium. So let me start by giving you a brief overview of the different steps in the discovery process. So through their analysis of a range of minerals over the course of many months, Marie and Pierre Curie found two fractions of the minerals considerably more radioactive than uranium, which was known to be present in the mineral. And the radioactivity was measured through the currents the mineral fraction produced by means of an electrometer. And they found two such fractions, and they eventually proposed that there were two new elements, since that kind of activity could not be accounted for just by the presence of uranium. The first was called polonium, after Marie Curie's native country, Poland, and the other one, radium, after the word radioactivity. But the interesting part is that these substances had not yet been isolated from the mineral fractions, and an identification through atomic weight determinations had not taken place because there were very small amounts of material. And in the case of radium, spectroscopic evidence was put forward already in 1898, the same year, but the spectroscopic evidence for polonium was inconclusive. Therefore, the team decided to direct their efforts towards radium, since they were more likely to succeed with that element. And after 4 years of intense work, in 1902, the team succeeded in separating a radium salt, and the metal was isolated only in 1910. So, although the discovery history of radium is well known, at least the main points that I listed now, less is said about the process. So how were the chemical analysis of the mineral residues carried out? This part of the history of the discovery of radium has been vaguely described, even obscured, I would say. So indeed, Marie Curie herself, in her biography, emphasized how important it was to have collaborators, and that at one point she and her husband and their team realized they could not make any further progress without the help of industry. So industrial collaboration was initiated already in 1899. But before I say a few more words about that, let me explain this photo. This is from the Nobel Museum in Stockholm, when they had an exhibition celebrating the centenary of Marie Curie's second Nobel Prize. And all the stone we see is supposed to represent the tons of mineral that was dumped in the backyard of their laboratory, and which they and their team were supposed to analyze through thousands of steps to obtain only 0.1 milligram of radium. So this is an enormous amount of work, and it illustrates also why it was needed. This industrial connection was needed. So the importance of the collaboration with industry has been well described by historian Xavier Roquet, but it has been toned down in biographies, even ignored in biographies of Marie Curie. The same goes for the production of metallic radium. It seems that it didn't have any significance, except in the biography of Marie Curie written by Robert Reed in 1974, where he described her work to produce radium metal as an act of utmost importance. But this has not been picked up in later biographies, and also not in popular accounts. Rather, the discovery histories tend to stop with the isolation of radium salt. Like it was then they had reached definitive proof that radium existed and nothing more was needed. But there were actually doubts about the existence of radium as an element in the community, and therefore producing the metallic form was very important to Marie Curie. And also the Nobel nominations for her second Nobel Prize was for this particular achievement. And likewise, Marie Curie never stopped thinking about polonium, and making efforts to prove its existence by different means was very important to her. So let us look at some of the chronology of polonium and compare it to that of radium. The main reason that polonium's existence was difficult to prove the normal chemical way is its occurrence, which is only 0.2% of that of radium. So it was very, very hard to obtain sufficient amounts. But Marie Curie never gave up. And she also learned that other scientists who had access to samples started to investigate the properties of mineral fractions and making similar descriptions of what she had called polonium. So this made her even more determined to isolate and identify polonium as an element to set all doubt aside. So she and her team, they made a lot of effort, but were most often unsuccessful in obtaining sufficient amounts, with one exception. In 1910, they managed to obtain a quantity of 0.1 milligram, which made it possible to get the spectroscopic evidence. And over the years, a powerful supply of polonium was gradually built up at Marie Curie's Radium Institute in Paris, led by her daughter Irene Curie. But the first large amounts of polonium were not produced until March 1944 in connection with secret work done for the Manhattan Project. And the intention was to produce polonium for an implosion bomb. So in the same way as the Curies collaborated with industry to concentrate radium in the early years of the 20th century, the industry also became involved in the isolation and preparation of polonium for the Manhattan Project. And the last point in this chronology is the atomic weight, which did not enter the International Atomic Weight Table until 1949. So the sentence I show you here, Marie and Pierre Curie discovered the elements polonium and radium in 1898, is something you can see in many textbooks and popular accounts. And even when I am asked myself when were these elements discovered, I would say 1898. This is the standard or the master narrative. But much is missing from this statement, which can be found in all these accounts. Like in many discovery tales, this one also involves heroization of historical actors and idealization of scientific processes. But I suggest that the particular context of radioactivity research makes the history of the discovery process even more complex than is often the case with element discoveries in general. First, we see two clearly under-communicated aspects of the discovery process, that the Curies were working in teams and that they were dependent on industry to achieve their goals. Then there is the matter of the year of discovery. If we choose 1898, this was the year where the particular radioactivity of the two mineral fractions was detected. But by selecting this as the discovery date, the hard work involved in and the significance of obtaining the first decigram of radium salt is under-communicated and undervalued, as is the production of metallic radium, which is what Marie Curie actually was nominated for her second Nobel Prize. And the contrasting fates of radium and polonium adds to the nuance of the discovery history. It is indeed two rather than one history. While the radium story itself includes many steps and spans more than a decade, that of polonium far exceeds the former in time and complexity. For this reason, and probably because the story of polonium has no easily defined endpoint, the polonium discovery is rarely included in any history of early radioactivity. Due to its scarcity in nature and its rapid disintegration, in the beginning, even Marie Curie herself expressed doubt as to whether it could be an element, since the spectroscopic evidence was inconclusive. And moreover, and this is my last point, there is nothing to suggest that Marie Curie's cardinal goal, namely determining the atomic weight of polonium in the traditional chemical analytical way, was ever accomplished before the new era of nuclear science. And then I will leave the floor to Brigitte and the case of element 43.
Thank you, Annette. Do you hear me? Yes? Okay. And I think I have control of the video. So I will concentrate on what I have called element 43 and the many instances of element 43 looking backward retrospectively. So in every textbook and reference book or even websites that are really professional or aimed at chemical references, technetium is presented very clearly as element 43 with all of its isotopes radioactive. It was first synthesized in 1937 by Perrin and Segre in Palermo, with actually material coming from California, and named in 1947 after Second World War with a Greek root meaning artificial. Now, earlier claims are also often mentioned in those presentations, including, for instance, the Commission for Atomic Weight and Isotopic Abundance. And those two claims that I'm showing here from Nodak and co-workers 1925 and Ogawa 1908 are actually well-researched cases in the history. Moreover, there are earlier claims of other putative elements that were contenders for element 43 or Eka manganese or a metal from the platinum or tantalum group. So I just want to note that I'm taking element 43 as the object, which I use to go historically backwards, with knowing very well that Ogawa, for instance, was thinking in terms of Eka manganese, and that before the periodic table, it was even described differently. What I also want to point it out here is the fact that this is a kind of response to what you can find in the literature as biographies of elements. And I will investigate, well, I will provide you details on 3 instances of these claims. The one on masurium by Nodak and team, the one on nipponium by Ogawa 1908, and the davium, which made our friend Frank James so happy. There are other instances that could be research as well, and which are more investigated in the chapter I offer for the collective volume. And I will be going backwards, so making sure that we are grounded in our times, and you will see later how that unfolds and how it explains how telling stories are contextualized. So the first act is rehabilitating masurium. In 1988, there was publication by Belgian radiochemist Peter Van Asse from KU Leuven on the ignored discovery of the element Z equal 43. He argued that the team from Berlin, Walter Nodak, Ida Tak, and Otto Berg, should be credited for the discovery of element 43, which is now called technetium. And indeed, he went on to a rehabilitation crusade. So I'm really taking the words out of his mouth. And as you see here in an excerpt from General magazine in German. And in 1925, Nodak and team argued or claimed they had found 2 manganese homologues, element 43 and 75. They named it masurium and radium. Radium has been accepted by the community after 5 years of producing metallic rhenium, very much the same story as radium, while masurium was never confirmed by the team. In fact, they were still looking for natural masurium after the Second World War, even at the time when technetium had been accepted on the IUPAC list of elements. Now, what is the pieces of evidence on which Van Asse rests his case? It is basically the argument that Nodak and team have seen element 43, which because of its nature of radio element was completely elusive, And therefore, if they have seen it and they have published it, it should be recognized and acknowledged as the first instance of element 43. Vanessa used the publication of a spectroscopic photograph, X-ray photograph, which is given on the second from the right. The first one is not the original, which has been broken and lost. And from that picture, he infers that the given material, the material as it is described in the publication of Nodak and team, it is very plausible that they have seen it. Now, he does that by counting the grains on the reproduction of the photographic plate, which was lost. And of course, with the knowledge that masurium, or so-called masurium, should be found in uranium ores. So this is very much a reconstitution, and as such has not been accepted by the chemical community, even though it triggered a lot of discussion. The second case, reassigning niponium, is something that appears a little bit less than 10 years after, by the hand of Kenji Yoshihara, also a radiochemist from Japan, who revisits the work of Ogawa, Masataka Ogawa, Japanese chemist, as the name indicates, and wants to reassess the discovery of a claimed discovery of niponium. So Masataka Ogawa in 1908 claimed to have discovered one and actually two elements. At first, he described it as the potential Eka manganese, so the missing element in the periodic table under manganese. And then waiting for spectroscopic evidence, which he couldn't provide for lack of material instruments. It waited until his death, that is, that the spectroscopy evidence was provided in the 1930s, a little before he passed away. Yoshihara's argument is that, in fact, Ogawa didn't see Eka manganese, but manganese, that is not technetium, what we call technetium, but radium. And he rests his case on a very minute observation of the publication, but also on material that has been gathered over the 25 years since his first publication. And here is the piece of evidence provided that has been actually worked also with historians and chemists. First off, the material procedure to refine, to make sense of the properties and in link with the ore from which it is extracted. Second, in the middle, you can see the spectroscopic data that were from the original samples, which, by the way, were kept. And later on, the reinterpretation of the spectroscopic evidence and also samples, which leads to the conclusion that indeed niponium, well, not niponium, but Ogawa saw definitely a new element. He mistakenly thought and attributed to be Eka manganese, and in fact, he had seen uranium. So the interesting part of this story is the reassignment of the discovery and the vindication of the discoverer who had been pushed away from the pantheon of discoverers. The last case, Davium, goes even further back in time. That is the alleged discovery of by Sergius Kern from Russia, who claimed he had found a new element in platinum ores from Russia and decided to name it Davium in honor of Humphrey Davy. By the way, this means that the name might as well not be used later on because it has been associated with a claim that has not been acknowledged. So that's kind of a problem. And I'm giving you two excerpts of his short notes, which were first sent to the Académie des Sciences in Paris, and then abstracted and further shared with Chemical News, the journal of William Crookes, where you can actually find a lot of other claims of new elements. Now, it was soon discussed and not acknowledged. Furthermore, he was not able to isolate sufficient quantities to share it with others, and others were not able to reproduce the results, mostly by not having the same ores at their disposal. However, much later in time, that is in 1950, two British chemists, Newton, Friend, and Drews, came back on this claim and looked at davium as a possible precursor for radium, even though, as I said, Sergius Kern himself thought it would be the element proposed by Mendeleev, placed between molybdenum and ruthenium, so under manganese. I will not go into too much details in this case, but basically we see the same elements, if I may say so, of pieces of evidence at work. Kern is eager to provide some properties of the metal, more actually than the atomic weight, like spectroscopic evidence, properties such as solubility. And also there is an ensuing controversy about how much of a discoverer he is, since the element was kind of predicted or suspected to be to have to be isolated, while the platinum metals were such a rich place to look for new elements, even more with Mendeleev's periodic system. Now, in their vindication, if I may call it, of Kern, both Friend and Drews argue, based on these properties and this material, since it's published material, they don't have access to the actual ores, they argue that probably this could have been dvimanganese, or rhenium, and that in this case, it would go a long way towards substantiating Kern's claim to have discovered a new element. So Kern's honor is saved, even though this is no more element 43. Now, I want to reach the concluding remarks since time is flying by. We have offered here two contrasting cases of telling the stories of discovery of elements in the time of radioactivity, and also how these stories look back in time, trying to find precursor and to vindicate claims from past chemists. And I want to go back to the picture that Frank offered to illustrate this presentation, which actually was an excellent choice. In some way, it pictures discovery and encapsulates some aspects of these traditional storytelling that surrounds discoveries of elements and discoveries in general. First off, there is a defined object one can contemplate in the case of radium, which is mostly pictured here. It's really some things that lights up the the place and also captures the site of the discoverers. These are clearly identified. There is a strong bond between the object of discovery and the discoverers. So that's it symbolizes the appropriation attribution process, and it refers to an expert practice. Those chemical vials and instruments on the site are a picture of that, which of course makes us laugh, because basically what helped to identify radioactivity were more physical instruments. But it says nothing about the community surrounding those discoverers. It says nothing about the long chronology and the complexity of the discovery, as Annette has shown for the case of polonium and radium. And this has to do with the way chemists themselves speak of discovery. For Partington, a chemist historian, things seem really straightforward. The meaning of discovery is well known in chemistry, he writes. When a substance is prepared for the first time by a clearly described method and sufficient details are given which distinguish it from other substances, it is said to be discovered. Plain and simple, as it seems. However, later, Rank Madsden, also a chemist historian, insists that this requires a closer look and a more detailed definition. So a discoverer is acknowledged when, I quote, he has observed the existence of a new substance which is different from earlier described substances, and this new substance is recognized by him or later by scientists as being elemental. Here we're talking about elements. Interestingly, there is an implicit disciplinary consensus on methods and results, which, as we know, appears not to be so consensual in case of controversies. And also the interesting thing is the introduction of the individual in the attribution. And it's a he, no comment. Furthermore, Rank Madsden insists on the fact that this has to be publicized and shared with the community, and at some point acknowledged by the community. So it has to be noticed by contemporaries, he writes, outside the immediate circle of the discoverer, usually in a periodical or a monograph, and he, again, must have made it the subject of a lecture given to a professional group. Later, this importance of publicity and community will be expanded by Kuhn, who insists that any discovery is actually a complex event. So this comes to the point that articulating the individual and the professional group is a key element, and therefore there are difficulties in pinpointing a date. Back to our two contrasting cases. Polonium and radium are two different stories, as Annette has very well described. And the story of polonium is much less known as the well-known or so-called well-known radium history. And the interesting in this case is that those two elements can be the story of these elements can be told in a way that keep all other usual parameters aside. Usually you have different actors in discovery stories, different sites, sometimes different disciplines are involved. In this case, the whole story or the whole narrative arc is around Marie Curie and her team. And the only exception in this case is the evolving definition of what is an element and how to identify or produce it and produce the pieces of evidence to make it real to the whole community. it certainly exemplifies how discovery is a process, and it demonstrates that discovery is not a linear process, except maybe when narrated retrospectively. Now, when we move to the many lives of 43, the question is not so much when the discovery is complete, but when is the history of the discovery complete? And actually, it is never. Discovery is not only not a linear process, but it is a historically situated process, and telling the stories of discovery itself is a contextualized process. The vindication of Ogawa occurs at a time Japanese chemistry and Japanese history of chemistry are sufficiently evolved to look for precursors and heroes of the national science history. Now, why does it matter to others than historians of science? This loops back to the introduction. This is important because this is the history of science that the general public and even chemists and students in chemistry get. Much of our book is inspired by Simon Schaffer's realization that discoveries are made up in the course of making disciplinary histories. And I quote, "The process of making up a discovery involves specifying its author, its location, and most important, its content." We want to argue that the making up of discovery also involves the context of narration. That is, when is the story told and for what aim, and for what reasons. And we want to argue, I quote, that discovery is a process, but that this process is constructed, deconstructed, and reconstructed while it is narrated, no matter the targeted community, from scientists themselves to the students in science, to the general public, and to the school setting. So this is why we based our book, forthcoming collective volume, Discovering the Elements, No Simple Stories, on questions such as what is a scientific discovery, what place have discoveries had in scientific and popular culture and education, and what a discovery means and how it is presented to historian, chemist students, or a general audience alike. Our forthcoming collective volume offers 9 cases on the following elements: yttrium by Charlotte, Abne Salomon, chlorine by Perret Grappi, aluminum by Sarah Hymans, radium and polonium by Annette, Lykknes, germanium by Gisela Buck, element 43 by myself, nobelium by Anne Robinson, heavy hydrogen isotopes by Helge Krau, and finally a chapter on argon, helium, and neon by Harman Junta. Now, added to the new insight on those discoveries and what we can learn on what discoveries are, we wanted to have an action item, so to speak. That is that every chapter is opening on teaching suggestion for the classroom, or at least for the education of science teachers. And this is how we believe that we can help to fill the gap between historians of science in general and chemists and teachers, science teachers. Surely this is not the end, because discovery is a topic and elements are 2 topics that have a long historiographical and publishing life. But this is the end of our talk, and I thank you very much for your attention.
Frank, you're muted.
I thought I had muted. Okay, so thank you both so much for that. I mean, that was a really meaty seminar that sort of has provoked a lot of sort of questions in my mind. Those, and I will use my usual chair's privilege of asking the first question. But anybody else who wants a question, please add it to the chat, and I'll call you forward. Just say you want to sort of ask a question. So I'm not quite sure where to start. How about with the periodic table? Because Annette, particularly, how influenced by the periodic table were the Curies? Were there obvious gaps where radium and polonium might be, or did it not play much of a role to them?
There were gaps that these elements filled that were predicted, but I have looked for explicit mentions of the periodic system in the material from the Curies, but I haven't found it.
Do you find that surprising?
Yeah, a bit, yeah.
Right. So Jonathan Ayling has sort of said, what a good talk. He feels sympathy with polonium. It's such a short, hard life. It must be hard to identify. But nobody else has put a question in. I mean, I noticed that one of the elements you're talking about is helium. Now, helium is a really peculiar one, isn't it? Because it's got detected on the sun during an eclipse and not found on Earth for about sort of 25 years later. So how are you approaching that?
Actually, Carmen is in the audience, I think. Do you wish to say something yourself, Carmen?
Yes.
Yes, I think I approached the detection of the spectroscopic lines fairly lightly and talked more about the isolation of helium as a tangible object, or at least an object whose spectrum could be measured on the ground and manipulated. That's a very interesting question, because in my mind, the detection of the spectral lines can be clearly related in retrospect to the tangible object, found later on Earth. Whereas some of the examples that Brigitte had mentioned seem either to belong to different elements, or in the case of the 1877 claim for davium, I don't know where those observations lead, and so don't know if I were writing the history that I would include those irreproducible and possibly disconnected claims.
Yes.
May I
sorry,
answer on this? I think you raise an excellent point, Carmen, about disconnected claims. And my point is actually in looking at the way elements are presented like universal and always existent entities that are waiting there to be discovered in the so-called element biographies. And then you can find all these earlier claims that either are vindicated or not later on, and also potential precursors. So I thought it was really interesting to look at how and by which historical narrative those come back into the stories, and how it thickens the plot by not only focusing on the context of discovery, but also the context of narration. So why all of a sudden this gains traction, why all of a sudden this is important, and what it does mean, not only about the discovery process, but about the nature of science. And in this case, things that are apparently disconnected are connected by the historical narrative. And we need to also make sense of that as historians. And we also need to warn or to make scientists reflective of this kind of practice that they actually have over and over again. So that's the more broader perspective.
Annette, do you want to say anything on that? Right. Okay, so Sarah Hyman has a question. Sarah, unmute yourself.
Thank you. And I first want to say, Brigitte, that was such an interesting reflection, and I completely agree that it's really interesting also to think about how these elements are seen as completely constant, even though some of the samples that people historically were dealing with are maybe not pure at all, and how this purity is dealt with then in the context of narration. But that was actually not my question. So I wanted to ask Annette, I thought that was so interesting in the story that you told of radium, I believe it was, where there was this really big quantity of material to go through before they analyzed a small, before they were able to isolate a small quantity of the element. And it made me think of a very similar story when Bunsen discovered cesium, and there's also this kind of heroic story of he had to go through so many thousands of liters of water in order to be able to find finally 1 milligram or something like that of the element. And I was wondering, well, first of all, if you know more about maybe Bunsen's case. I know it's a completely different story and context, and whether there were similar things of who was helping him. Did he do that all by himself? I never really read anything about
I don't
this.
know that. I am not up
Okay,
to
yeah.
speed with that
It was
case.
kind of a long shot. But then also I wondered, how did the Curies deal with this aspect of the story? Did they present themselves as the people having done all this work, or did they actually really acknowledge
It's
the work
a
that was
bit
behind?
contradictory because Marie Curie wrote this biography of her husband, and then she has also some autobiographical notes in that biography. So on one page, she can say that this is the point where we were working all alone, and it was so hard, and this is the kind of quote they pick in biographies and popular accounts. But then if you go a few pages further, then she can say it was so important that we had this. We employed, for example, Gustave Beaumont, one of the collaborators, and that we had all this big team. So they contribute to, or she contributes to both parts of the story, so to speak. But when I showed you the picture from the exhibition, in the background you also saw a quite famous picture of Curie stirring some material, and this is also used to reinforce this image that she was working hard alone, doing all this stirring with all the tons of minerals all by herself. So there are, but when I looked into it, they started with like 20 kilos between themselves, and then when it went further, or they connected with the industry, so they just started with the first small amounts to sort of establish procedures and to do some test materials, and then they couldn't, of course, they couldn't cope with all these tons.
Annette, sorry, Brigitte.
Oh, I just want to add something that Annette said, is that Marie Curie provides stories herself. So the narrative process starts very early on by sometimes the actors themselves, sometimes not. It is, of course, again, as historians, it's of course really important to be critical of the way they report their own findings and to go beyond the very dry aspects of a publication, which in this case, Annette points to biographical accounts or autobiographical accounts, and I think this is the case in many instances. And then it's also the case that not only she insists on the work being done, but this is a trope within the community that is accepted to be used as a heroization process as well. So there's a whole social game there at play, which we need to be critical of, and which I think the scientists themselves take for at face value. Sorry.
I mean, just going back to what Sarah was saying about Bunsen, cesium, and rubidium, it's really interesting reflecting on sort of what I was doing 40 years ago when I did do some writing on Bunsen and those two elements. It never ever occurred to me to ask as a question, how do you actually reduce, I think it was about 10,000 liters of Durkheim mineral water to sort of get at these two elements. And I think that just shows how historiography has moved on in that time. My suspicion is that Bunsen had an awful lot of students at Heidelberg, and he just simply told them to go away and evaporate all this mineral water, and we'll sort of deal with the residue. But I don't actually know, because, as I said, it would never occur to anybody at that point in the sort of mid-80s to ask that sort of question. So I would think that's progress of a sort. Not that I believe in progress, I have to say. Any other questions coming through? Okay, well, can I just go back to another element I worked on at one point, and that was thallium, which William Crookes discovered, first of all, spectroscopically, and then isolated salts of it and showed it sort of chemically it did produce different reactions to anything else, and it was therefore a chemical element. But he didn't produce significant quantities of the element, and it was actually Lykknes in France who did that first. And then there was this god-awful row in 1862 between Lykknes and Crookes as to who constituted the discoverer of thallium. And Crookes was absolutely determined to come out on top as the discoverer, because that made his reputation. Got to that point, he'd just been a sort of a scientific journalist, but he clearly wanted a better career than that, and he saw thallium as a way of getting that position within the scientific community, elections, especially for the Royal Society of London and so on. So there were a lot of social negotiation going on to construct that chemical element. And I'm just wondering whether in the case of the Curies, backdating it to sort of 1898 was a sort of way of making sure that the discovery was theirs and not someone else's, so making it unambiguous. It's the Curies' work.
By the way, Frank, I did put something in chat at 1749.
What's 1749?
You said there were no more questions. There's one I put in chat at 1749 on the list.
Yeah, okay, that's only just come up on my screen.
Oh, right.
Right. So do you want to ask it, Mike?
Well, it was simply that the paper by Rayleigh and Ramsay of January 1895 is a contemporary account. You know, they'd only just done the work, and it seems beautifully complete to me, followed by a little paper by Crookes, and it includes an acknowledgement of Cavendish. Is argon a case that proves that sometimes it may be simple?
Did Cavendish publish that work?
Yes, well, certainly when Rayleigh and Ramsay wrote the paper, they say, I don't know whether they discovered it after they discovered argon, they said that Cavendish had reported a little bubble of argon, a little bubble of something which he could not get to disappear when he sparked it or whatever. But of course, he had no spectroscopic means of characterizing the material at the time. But their own paper seems to me incredibly self-contained, incredibly contemporary. And although they probably had glass blowers and things to help them, I suspect it was mainly their own work.
They would have had, well, Riley would have had access to the Royal Institution's laboratory and all its equipment and apparatus and assistants and so on. Annette, Brigitte, any comments on any of that?
Annette, you want to comment? No? Okay.
No.
Just one, I think one point before passing it to Carmen, since it's about argon, it's just this kinds of makes or reinforces the point I was making about precursor, the fact that Rayleigh and Ramsay wanted to signal or acknowledge Cavendish observation, even though, of course, Cavendish is not looking for a new element. He just observes something that he sees is different from all he can relate to. And I think this is, it seems like it's historical, but to me, this is very much a scientific way to proceed backwards and in time, and kind of unite the community over the centuries in ways that gives credit to a chemist of the past. So, but anyway, I'm just leaving the word to he wants to say something about argon.
Carmen.
Yes, so going back to Cavendish does make the story longer, and Rayleigh in particular, updated a method that Cavendish had used, sparking, to try to collect more and characterize the little bubble. But the other bit of complexity on the argon story that I talk about in that chapter is the debate that followed this 1895 presentation about whether argon was really a chemical element if it didn't react with anything. There were some questions as to whether it was possibly a trimer of nitrogen, but even accepting argon as something not previously discovered, did it belong to chemistry, was a question that was debated at least for a little while afterwards.
Although, of course, in that case, there was not a gap in the periodic table to put it into. They had to create an entire new group. And in fact, Julius Thomson was very important in that.
Okay. Alexander Angerhofer, you have a question.
Yes. Can you hear me?
Yeah.
I'm curious whether Madame Curie ever found evidence for other isotopes of radium. I understand that the isotopes were discovered later than when she made her initial discovery. I think it was Frederick Soddy in the 1910s that discovered isotopes. But did Madame Curie ever go back and look for isotopes of radium?
From the top of my head, I don't have a clear answer on that, but I know that in the lab, she and her students or the group, they were doing atomic weight determinations always, and that's when you find out that it's a different isotope because it's the same element, but it has a different atomic weight. So that they did that for many elements, but I cannot say for sure that they did it with radium from my recollection. Yeah.
Thank you.
But radium, of course, when they were mapping, one of the most important things they were doing in this period before the 1920s was to map these radioactive series, and then radium appears several times in different versions. So I would, but that happened also in other labs, not only in Paris. So exactly who did it, I'm not sure.
Jonathan Ayden's got an interesting point. Jonathan, do you want to sort of make it?
Yes, I was just speculating about why people become heroes and heroines. And one element is, of course, obviously we love a good story, but another one is just the sheer danger of chemical research, which is exemplified by the Curies and their premature death. But I was also thinking of fluorine, which had took a terrible toll on the people trying to isolate it. So I wonder whether, in a way, some of the heroic tales aren't slightly justified by what these people went through.
Yeah, you're right. But the problem with these stories is that you also limit, or you not only say they were heroic in that sense, but you tend to leave out all the complexity, and you just show the things that were successful and the things they had to go through. Yeah, but it's a good point.
Okay, Peter Oakley, and I think we'll make this the final point before wrapping up. Peter.
Hi, I've dropped something in the chat. Sorry, I'll put my video on as well if it will work. I've dropped something in the no, there we go. I've dropped something in the chat talking about the wider aspects of this, about scientists being identified in public as experts and how that comes through the acknowledgement of their success in a project, so that there's a something wider to fight for apart from just within the scientific community. And I've flagged a recent example of Whitty's sort of the acknowledgement that people believed him far more than any politician during the pandemic because he was a scientist with status. So I think this connects to some of this, people trying to accrue this status in the discovery process, and there have been a couple of mentions here. So I wonder what your thoughts are on this, because very complex stories are then very difficult to translate. So flattening something down to acknowledge that somebody had a leading role in this actually can be quite important. But saying that, I'm aware that that tends to remove other people from the picture.
Yeah, I am sympathetic to and to why people do it, and when you're trying to really condense a story and you have to just give a point, you have to simplify it somehow, and then if you add all the complexity, it's going to be too long and too uninteresting, maybe even for the audience, the target audience. I don't know if that was what you were.
I suppose my question is, if all we say is yes, it's a lot more complicated, and actually the people we're lauding aren't really as important as they are, it sort of collapses the house of cards without not providing something else, and damage the wider thing. That's why it's sort of, how do we see our way through to the other end, rather than just say what's there is not right.
Yeah, I guess the trend has been for many years to also show the contributions of people who are not like the main characters in the normal histories, and that's as important as showing the one that maybe won a prize or did a key discovery, because it always involves more people and more steps, and so I don't see this as a problem. Adding more people that will diminish the contribution of the hero. Maybe Brigitte wants to add something.
Yeah, I of course concur with Annette in the assessment that this does not diminish the contribution of some who are already credited, adding other people in the picture. As long, of course, it's not trying to overturn the traditional narrative and say, for instance, Marie Curie stole the discovery from XYZ. But I think it addresses a wider issue, which I would like to frame in this case in the teaching of the nature of science. It is important to convey to the general public and to citizens, and especially to future scientists, that you are not living a life in science for nothing if you're not a discoverer, and that you are bringing something fruitful to a community. So I'm going there because most of the discoverers are always, especially Marie Curie, then used as role models to attract youngsters to science, and to some extent it might be hypocritical because there is no place for making a discovery every day or even in every professional trajectory as such. So I think it's important to bring out these stories and explain how you can be relevant and meaningful to a wider community, contributing to a richer narrative on what it is to make science, to do science, and to gain knowledge over the unknown. So that would be my rationale behind the fact that I don't think it would collapse the role of scientists or the social status of scientists.
Yeah, I mean the science is so much more than just discovery. I mean, discovery is obviously important, but all sorts of other aspects, as you say, Brigitte, feed in to science. And a lot of the heroic narratives of science from the sort of 19th century down to the sort of present concentrate on people's research and not on, I mean, for example, 17% of all of Faraday's letters written after 1836 are on lighthouses, which has never been written up before, yet it was clearly a very important part of his life, and that was still science, and that's sort of just been neglected. So the other point I would add to that is it's really important to understand historically how the historiography of particular people's reputations were built. Why is it Curie who gets the publicity? Why is it Davy who gets the publicity? Why is it Faraday who gets publicity? Those sort of issues do need to be understood. And I think the point, Annette, about telling these stories is it's the tone. I mean, there's nothing worse than writing a patronizing story for the general public. You've got to get the tone spot on, because if you don't get it spot on, people will be put off. So I think from what I've heard today from both of you, your tone is spot on, and I'm looking forward to seeing the book. When is it? Was it due out?
End of the year.
End of the year, right? Christmas presents coming up. So I think with that, I'll draw things to an end. Just 2 or 3 announcements. As many of you know, SHAC runs a grant scheme. We're still accepting applications for grants to support research, meetings, the sort of normal sort of academic activities. And if you want to form, email grants@ambix.org and one will be sent to you. The next seminar in this series will be on the 11th of July, when Peter Morris will talk about his and Peter Reed's biography of Roscoe. I'm not quite sure whether it'll be published by them, but the publication is imminent. And the SHAC autumn meeting will be on the 11th of October in Amsterdam, and the call for papers will be issued fairly soon, I am assured. threatening emails would be going out soon if it's not. Now, seminars like this don't just happen by accident. There's a lot of work by a lot of people to sort of produce these, and so I'd particularly like to thank Rob Johnson, Anna Simmons, Caroline Cobbold, Becky Martin, Chris Campbell, and Joe Hedison. But above all, thank Brigitte and Annette for giving us a really, really good meaty talk, provoked a really interesting discussion. So thank you so much, and have a good evening or day or wherever you happen to be in the world at the moment. Thank you.